By this stage, you might be wondering why we're talking about these mechanisms, easy as they are. I hope you're happy with what we've talked about up till now, in the chemical kinetics section. And the answer is the fourth really important rule of a multi-step mechanism is that one step will be slower than all the others. That's the one that determines the rate of the reaction. That is the one that leads to the rate law. Now, if we go back and consider our favorite multi-step reaction, right, this two-step reaction that has those steps there, okay? Now, the slow step of this one is the first step. You can possibly intuitively answer why that is. First step involves breaking a bond. Breaking a bond, of course, requires some energy. You've got to have a big collision going on in order to break that bond. The second step is just where you get a cation, comes together with an anion. You'd say, well, that's probably a nice, easy thing to have happen. It still requires a little bit of energy, as we'll see in a minute, because you've got to rearrange some geometries going on here. But by and large, this is a nice thing. This requires energy to break a bond. It's kind of a nasty thing. So let's focus our attention on this slow step of the reaction. Well, that slow step of the reaction involves one molecule of CH3 3 times CBr. So in other words, if we double the numbers of CH3 3 times CBr, we'll probably double the rate. If we triple it, we'll triple the rate, because that first step involves the CH3 3 times CBr banging into something hard enough to break that bond. Increase the number of those, you'll increase the number of collisions that have the same proportion of good collisions, so you'll increase the number of good collisions, increase the rate. Okay, thus we can say that it's first order in CH3 3 times CBr. Now, how about the Cn minus, the other reactant in a reaction? Well, this other reactant, Cn minus, isn't involved in this step at all, and therefore we can say it is zero order in Cn minus. So by just considering this mechanism, saying that the first step is the slow step, we say the rate is K times the concentration of CH3 3 times CBr. First order in CH3 3 times CBr, because that's the thing that's doing the banging into stuff. Zero order in Cn minus, because it doesn't get involved in the reaction until after the slow step. Now let's draw a pretty little reaction coordinate diagram associated with this. Energy up the vertical, reactants on the left, products on the right. And of course, where we've seen this before is for a one-step process. We just go over the activation energy hump and down to the products. But this case here, of course, we've actually got two steps. So we will see that there are two humps. The first hump is where we start off with the reactants and we go through step one. Step one, where just the CH3 3 times CBr bangs into something hard enough to break that bond. Okay, and so after it's done that, we hit this intermediate point where we got the intermediate itself, CH3 3 times C plus and Br minus, and we still got some Cn minus floating around that we haven't used yet. Now, we said this is the slow step, this is the hard step, this is the step that's going to need the energy. This is the step that has the highest activation energy. Okay, get over that activation energy, then the reaction can happen. So now the second step here is still going to be a little bit of a hump, okay, because you've still got to rearrange some things, still got a little collision, so that rearranges, still need a little bit of energy and so on. So it's a little hump for step two that goes down to the products. But step one, the slow step, has the highest activation energy, is the highest hump. Okay, think of a roller coaster here. You haul the car up to the highest point, and then it lets go, and it's got enough energy to take it down over the second step. The first step, highest end activation energy, if that first step is the slow step. Let's look at one more example. Nice reaction here, 2NO2 gas plus H2 gas goes to N2O3 gas plus H2O. Let's flip it from the other direction, right? The experimentally observed rate law is KNO2 squared. In other words, second order in NO2, zero order in H2. So right from there, we know it's going to be a multi-step mechanism, because one step is the slow step that doesn't involve the H2. The H2 therefore has to be involved after that slow step. So we could come up with a possible mechanism for this, in which we say, well, first of all, let's have 2 molecules of NO2. There's the 2 molecules of NO2 coming together to make an intermediate, N2O4, and then that intermediate, N2O4, reacts with the hydrogen that's got to be involved in the reaction, but it's got to be after the slow step to make these final products. Slow step, step 1, doesn't involve the H2, does involve 2 molecules of NO2. This is experimentally observed. This is what we derive from that theoretically. Drawing out a pretty little picture, starting with 2NO2 and H2 on the left, ending up with N2O3 and H2O on the right. First step, second step, first step higher than the second step because it's the slow step. First step, you go to the intermediate, N2O4, still haven't used the H2, then the H2 comes in to give you the final products. First step, the highest step, because it's got the activation energy that's highest because it is the slow step. That's the pretty little picture for that. Hope you enjoyed this particular bit. We'll talk more about this in class.